Hello, YouTube! The camera wasn't working, so we're starting again. We're going to talk about a problem where we actually approach it conceptually and then do the math, because the math can be pretty tricky and it's sort of weird, so want to make sure you've got an example of it. So, our situation is we have a thin metal rod, we know its length, we know its mass, so this is one where we're not using numbers, we're using variables, and honestly that kind of makes it easier for this. We've got a thin cable attached to the end of the rod. What are the forces on the rod? And which of them must be equal to each other? The last one is, what is the tension in the cable in terms of L, the length of the rod, M, and theta? We're going to do it a shortcut way, and we're going to then do it the normal way. I don't honestly remember what the shortcut way was, so we're probably just going to do it the normal way. Maybe I will as we go. So I'm going to swap to paper because this one's going to involve a pretty good chunk of work. Let's get some stuff written out. So I know the angle. Oh, yes, I figured out the shortcut way. And it won't work. So great. I know the angle, I know the length, and I know the mass. And what I want to do is find out what the forces are and which ones are balanced and which ones are equal, basically. So set up some equations for forces. First place I'm going to start is a free body diagram because that's a lot easier because I don't have to think about where things are happening. I might have to come back and add things to this after I start thinking about torques, especially because torques can have a pretty big impact on the way we think about the forces. So we got mg going down because of course we do. We're not going to have a normal force going up because it's not pushing against the floor or anything. But there is a rope, there's a force of tension, so we will need a force of tension. And we can go ahead and break that up into components. We've got our x component and our y component of our tension. So we've got Ft times the cosine of theta and Ft times the sine of theta. And those are the only ones I can immediately think of, but again, we might have to come back and add some more. So if I take a look over here, a little more zoom on them. Yeah, that should be a little more legible. Double checking, can people read that or is it like super blurry and stuff? I know some people have issues with connection. Okay. So if I draw those forces here, we've got a force of tension going like this, and we've got a force of gravity going like this. One thing that I want to check is because everything has to be balanced, I'm actually going to think about where the pivot could be and what that would change. And actually, before I even do that, really quickly, there is a big problem with my free body diagram. This needs to be balanced. So I must be missing a force from something going to the right to balance out Ft cosine theta. So I don't necessarily know what this force is, although if I look at the picture and think about it, the only thing that could be pushing this rod to the right is the wall that it's in contact with. If it's in contact with the wall can push it to the right because the wall's on its left side. So this is the normal force from the wall in the x direction. That might look like a really weird label, but it'll make more sense later. So the next thing I want to think about is where I can put my pivot and what that will do. If I put my pivot on a force, it'll let me ignore the torque from that force because that wouldn't make it spin around that pivot. It would just move it up linearly instead of angularly or spinning. So if I put the pivot in the middle, there's something kind of weird that happens. Gravity doesn't make a torque. I do know that my wall needs to be pushing it to the right, but this is pointing straight at the pivot. If you have a force pointing at the pivot, it can't make a torque. If I push my arm like this, it'll make it move sideways, but it won't make it spin. The only way that I can make my arm spin is if I push it from the side. If I push it at an angle that's not directly along the radius, a tangential centripetal component of the force. So we actually wind up needing one more force here, because if we look at what's happening, currently this thing has the force of tension causing it to try to spin out of the page. So like that. We have gravity doing nothing. We have the normal force from the wall doing nothing. There must be one more. And absolutely, it's from the wall. It's the normal force going in the y direction. Now that needs to go the opposite way or try to get it to spin the opposite way. I need it to spin into the page. R is looking like this, so I can either have it spin down, which would be out of the page, which would be backwards from what I want, or I can have it spin so that I point my thumb down, which would make it spin like that, which is into the page, which is what I need. So I need the force to go up so that it tries to get it to spin like this so that the two cancel out. So this is the normal force from the wall in the y direction. So there's also some normal force from the wall in the y direction. So if we're thinking about which of these things need to be balanced in what way, we can just use a Newton's second law equation, and that's actually not too bad. We can say that our net force equals 0 in each direction. That means that our normal force from the wall in the x direction needs to be balanced with the force of tension times the cosine of theta. And we know that the normal force from the wall in the y direction plus the force of tension times the sine of theta minus the force of gravity needs to be balanced as well. So this is our setup for our x, this is our setup for our y. We can also do a setup with our torques. The weird thing about the torque setup is instead of thinking about it as like xy, you probably want to think about it as, okay, I can put the pivot literally anywhere. What's it going to look like when the pivot's here? What's it going to look like when the pivot's here? What's it going to look like when the pivot's here? And every time you do that, it lets you ignore some of the forces along the way. To start out just by thinking about things that need to be the same as each other, I'm going to put the pivot on gravity. So when I do that, or in the middle, and this is a thing that we've mentioned but not talked about a lot, gravity is effectively coming from the center of mass. That's actually just sort of one of the really neat and useful things about the center of mass. There's going to be a torque from gravity, which is 0 because it's on pivot. There's going to be a torque from our normal force from the wall in the x direction, F on wall x. But that's going to be 0 because it's pointed at the pivot. There's going to be a torque from the y component of our normal force. And that's actually going to exist. It's going into the page, so I'm going to make it negative. And then we'll get a torque from our force of tension. Oops. All that needs to equal 0. Now, a little bit easier because this is 0 and this is 0, which actually does something neat because it tells us that these two torques must be balanced with each other. So let's say what else we can get that to figure out. Weirdly enough, it's going to be the exact same thing that we already figured out using the linear stuff, but spoilers, I guess. Remember that torque is a set of instructions. This is basically telling us to plug in RF sine theta. RF sine theta for each of these. So when we do that, what it'll look like is R, which in this case, for each of these, from the place I picked as the pivot, L over 2, L over 2. If I put the pivot in a different place, this will be different. So L over 2 times the normal force from the wall in the y direction plus, times the sine of the angle for the wall, which is 90 degrees, because this is perpendicular to the rod. Minus, what's this one? Plus L over 2 times the force of tension times the sine of theta. Well, these are in both terms, so we can just divide it and it drops. This is 1. This is just the same thing as this. Oh, no, sorry. No, it's not. It's something new. Sorry. Yes, right. This actually tells us that not only, if I add this to both sides, so plus normal force from the wall in the y direction, plus normal force from the wall in the y direction, this tells us that not only is our x component of the normal force equal to the x component of the tension, which we figured out using Newton's second law, using the torques, we actually figured out that the y components are the same as well. So weirdly enough, or maybe not weirdly if you think about the symmetry of it, because you need it to completely balance, and it's balancing around this mg, you need the normal force to be the exact same as the force of tension. In this specific case, that won't always be true. The other thing that's kind of neat about that, to me anyway, is because these two things are the same as each other, we could actually say that the y component of either of them must be twice as big as gravity. And that's the shortcut for this one, is because them together and they're identical balance with gravity. That means that each of them needs to be half as big as gravity. So for B, because we did all of that conceptual thinking, because we mapped out which things need to be balanced with each other, because we mapped out which ones need to be the same as each other and which ones are balanced aside from that, I could actually go ahead and say that double my force of tension times the sine of theta minus mg needs to equal 0, again, because the normal force from the wall and the tension are the same as each other, so it's like having two of them. So as a shortcut, I can do plus mg, divide, oh, sorry. For some reason, I forgot how to actually show my work. 2ft sine theta, mg. And then I just have to divide each side by 2 sine theta. And I'm all set. The force of tension will be mg over 2 times sine theta. So that's our shortcut way, using the stuff that we already figured out earlier. Sorry, it is actually kind of difficult to slide it up enough. Yes, perfect. So the less shortcutty way to do it is to actually change where our pivot is a little bit. The question says we're supposed to do it in terms of L, M, and theta. So to me, that says I want to actually use gravity, not ignore gravity. So instead of putting the pivot in the middle, I'm going to put the pivot on the far left, because if I do that, I don't have to care about normal force anymore. It's on the pivot, so it doesn't have any torque. So when I'm adding up my torques, what that'll look like is the torque from my tension minus the torque from my gravity. And just to double check, around this pivot in particular, tension is still trying to spin it this way. Gravity is trying to spin it this way. Those are opposites, so they'll subtract. And gravity is into the page, spinning your hand the way it's going to spin. Out of the page, spinning the hand the way it's going to spin. That needs to be equal to 0 because it's all balanced out. Once again, set of instructions. Plug in R, plug in F, plug in theta. I'm actually going to write them out this time instead of plugging it all in at once, because it's a little harder to see. Although I will say just immediately that sine for gravity is going to be sine of 90, so I don't really have to care about that. Now I need to look at the R's. If I go back up, for gravity, it's from here to here. So that's L over, that's way too high. It's not which way it's going to spin it's not which way it's going to spin, it's which way that specific torque will be trying to get it to spin. Does that make sense? So Are you trying to say how do you know where to put the pivot? Like, how do you know where it's spinning around? Or are you trying to say, how do you know whether or not this torque is trying to get it to spin into the page or out of the page, or like clockwise, counterclockwise? You're not supposed to use that because it's ambiguous, but where to put the pivot. Yep. The reason I chose to put the pivot here for the first time that I was doing stuff and here for the second time, to your point, it's not spinning, right? So does it make sense that it's not spinning around here, but it's also not spinning around here, and it's also not spinning around here, and it's also not spinning around here, and it like literally you can put it anywhere and it'll work. So you just pick the point that makes the math easiest. The question didn't ask us anything about the normal force. If I put the pivot on the normal forces, they don't make any torque, so I don't have to care about them, which makes the math really easy because it ignores the thing that I want to get rid of anyway. Does that make sense? Great. There was a question about why a ladder would spin. If you have a ladder that looks like this with no friction, gravity goes down, the normal force from the wall goes this way, the normal force from the floor goes this way. If I put the pivot here, then these two could conceivably cancel, although they won't. Because this will rotate like this will rotate like this, my thumb is pointing opposite directions, they cancel. If I think about putting the pivot here, they could conceivably cancel. This one tries to get it to spin this way, the gravity, I point at the force and then curl it the direction of the force, points into the page, we're good. If I put the pivot here, gravity is trying to get it to go up, this one's trying to get it to go down, they could conceivably cancel, great. The problem comes in with the sizes. If you think about Newton's second law for this one, we've got up, we've got down, we've got left. Could this possibly be balanced? In real life, how does the pivot apply? I'll talk about that in a sec. But could that possibly be balanced? Yes to going over the hand thing, correct to the no, it could not be possibly balanced. So because it can't be balanced, it has to be accelerating to the left. How would this ladder move to the left? Well, the center of mass has to accelerate to the left. Weirdly enough, also the center of mass has to accelerate down. But if you think about what that would look like if I just drew it, if the ladder is over here now, there isn't a wall anymore. So this part of the ladder now starts to fall because there's no normal force from the wall going this way. That means that it just goes down the wall. Well, it's a physical object with a set length. So in order for it to go down the wall and move to the left, the center of mass has to move from here to here, and it winds up going in like a circle. As far as where it's pivoting around, it isn't actually rotating in a clean circle, so the pivot is constantly moving. For this specific case, the pivot would actually be probably somewhere like here or here or here. A situation where you might actually have to know what the pivot is and like think about the pivot is, let's say that I hold a meter stick up and I balance a meter stick on the ground. And then someone gives it a little tap. When someone gives it a little tap, it'll now look something like this. Because of that, we've got mg going down, and a normal force from the floor going up. Now this one actually is spinning, and the point that it's spinning around is the point where it makes contact with the floor. So that would be your pivot. Does that make sense? Just like as far as where you would put the pivot when it's moving? Because when it's moving, it's really easy to figure out where to put the pivot. You can, so yeah, this was something that used to really bother me as well, so this makes a lot of sense that there are questions. You can choose where to put the pivot if it's not moving. Because if it's not moving, it is equally not moving around everywhere. As soon as it's actually pivoting, you can't pick wherever you want to put the pivot. It's actually like you know where the pivot is, it's pivoting around that point. Okay. As far as going over the right-hand rule again, yep, absolutely. One last time. I'm going to try it with a physical object and see if that helps, and you can then see which way it'll rotate. The only problem with this, and you know what? Now there isn't that problem. I was going to say I'm facing the different way from the object from you. Okay, so if I push this up on this side, what'll happen is the moment arm is from here to here, so that's the way I point my fingers, specifically my index finger if you want to do it the careful way. My middle finger needs to point the direction of the force, which is up. My thumb shows you the direction of the torque, which is towards you. So if I spin this, it'll rotate towards you. Now, towards you, away from you, probably not going to mean anything to you unless you've been doing a whole lot of rotational physics. If I think about pushing it down, R goes this way. I'm pushing it from the same point. If I curl, this is a second way to do it. If I curl my hand the way that the force goes, my thumb points away from you. The only thing that you need to know for that is that they're opposites from each other. Towards you, away from you. That lets you know that these two things are going to fight against each other. One would be positive, one would be negative. Traditionally, towards you is positive, away from you is negative. The reason I do it that way instead of saying clockwise or counterclockwise is when I'm looking at this, rotating this way is clockwise for me, even if it's counterclockwise for you. Rotating this way is counterclockwise for me, even if it's clockwise for you. If I take my hand, though, in order to have a force go up on it, from my perspective, I point at the force, I curl my fingers up, it still goes towards you. So if I say it rotates so that the vector goes towards you, they're going the same way as each other regardless of where I am, which is why that's useful. And again, the process for it is start at the pivot, point towards the force, curl the direction of the force. When you do, your thumb will point the way of the rotational vector. As far as the AP exam is concerned, you don't have to be able to tell them which direction the rotational vector goes. You just have to be able to tell whether or not two things will work together or fight against each other. If you draw the circle that it's trying to get it to go in and draw the directionality of that circle, that's a really easy way to do that. So in this case, it would be draw this circle when I try to push this way, right? When I try to push this way, if I'm pushing down, on the other side, the circle goes the same way. If I'm pushing up, the circle goes the opposite way. So on opposite sides of the pivot, pushing the same direction will cause opposite things. Pushing opposite directions will cause the same thing, would be another way to remember it. Does that help a little bit for the person who was asking about the right-hand rule before we do the actual final bits of the math? Yeah. Yeah. Yep. That would be because of wind. But oh, if you're saying if it was really tall? Yes. So this has to do with, oh God, I wish we could talk about this more. There's so many really, really cool ways to think about this stuff that just like involves actual math and like, wow, 3 is a lot. That's a lot longer than I thought it was. Interesting. Yeah, it might be different by person. We're talking about the Zoom delay for in person versus not. So if I take this thing and I try to balance it, the question was, why would this thing fall over but like a roll of paper towels won't? And the answer is, effectively, it has to do with locally stable potential equilibrium wells, or potential energy wells. And it's a really, really interesting way to think about things. So I'm just going to show it. You don't have to do this for the AP exam. You don't have to do this for this physics course. If it was physics C, we would talk about it because we get to talk about all the fun things that just involve really hard math in physics C. But basically what you can do is you can think of it as if you graph the potential energy as a function of position. Once I make that graph, for my really thin object, it'll look something like, I guess there's a much easier way to explain it. We'll start there and then we can apply that to the potential energy wells. If you think about the thick object, right? Here's my torque, or sorry, here's my force of gravity, here's my pivot. In order to get it to fall, I need to rotate this enough that the center of gravity is past the pivot. Because if the center of gravity is here, suddenly, right-hand rule, more practice on that, my torque goes into the page and this thing rotates like this, right? But if my center of gravity is over here from the pivot, the torque goes the other way. So if the center of gravity is able to shift over the center line of the pivot, it'll fall because the torque is accelerating it away from a stable position. And if you have it the other way, it'll come back to its original position. And so if you have things with a really narrow base, the distance from the center of mass to the pivot in the x direction is very small. So you don't have to move it very far for it to get over that line. If it's a lot wider, you have to move it a really big distance to get it over that line. The way to think about that with potential energy is if you think about the amount of potential energy the object would have based on how much you have rotated it. If you draw a graph of that, it'll look something like this, where it'll have 0 when it's over on its side, and then as you get it up to 90 degrees, it'll have more potential energy. But there's actually this weird thing where, does it make sense that as you rotate it, initially the dot actually goes up because the dot goes in a circle a little bit? So there's more potential energy to either side, and then you have this tiny dip in potential energy, and then it comes back down. To determine whether or not something is stable, what you can do is think about it as saying, if you give it a certain amount of energy, potential energy graphs are really cool because they basically show you which way the object will move if you think about the object as a ball placed on a hill shaped like the graph. So if I think about putting my object here, it'll oscillate back and forth as it just sort of rolls back and forth here because it's locally stable. But if I give my ball enough potential energy to or be at a position where it's hill this way. So this creates a locally stable well where if you displace it a little bit, it'll actually just rock back and forth in that little thing because it hasn't gone far enough to be on the part of the hill where it'll roll down the hill because it's like basically stuck in the little cauldron. The wider the object is, the bigger the circle, the larger that well, the wider that well is going to be. The narrower the object is, the narrower that well is going to be, and so the less you have to displace it. So the tiniest disturbances would get, if I was trying to balance like a meter stick without it falling, the tiniest disturbances will be enough to rotate it so that its gravity is providing a torque. So it falls. Mm-hmm. Mm-hmm. Yep. And technically speaking, if it was able to be perfectly like undisturbed, locally, like if you think about something that is like completely and totally infinitely thin, the graph will look like this, where there's just a peak with no valley at all. Technically, there is a point where you could balance it so that it is not moving, but that's considered an unstable equilibrium because any disturbance at all in any way, shape, or form will make it start to roll. So if you've seen some of the things where people have like these really crazy impressive things that are all balancing on each other and stuff, and it looks like it should be completely impossible, what they've done is they've managed to situate it, and I'll see if I can find the bird while I'm talking. They've managed to situate it so that the object has its center of mass directly above, so that there's a straight line between the center of mass of the object and the point of contact that the object is making with the floor. If you do that, the pivot will be below the center of mass, and it'll be stable. It looks crazy because that shouldn't, like, depending on which objects you're using, it's really counterintuitive where the center of mass is. I can't find the bird. Oh, thank you. It looks really counterintuitive where the center of mass is. And so that's the thing with this bird, is if I take this bird, the center of mass is located directly on its beak. So I can get it to balance on this pencil pretty stably because that's where the center of mass is, as long as I put the pivot so that there is the pivot it would be rotating around is directly under the center of mass because gravity can't make a torque on it. This is all good stuff, so as much as it wasn't originally what I planned, I'm totally fine with it. Does anyone have any follow-up questions on any of that or anything before we finish out the problem? We have a little bit more math to do. Okay. Last bit for the math. So looking at our difference in the distance from the pivot, because I can put the pivot wherever I want, and I chose the place that gets rid of the normal force, gravity is L over 2 away from the pivot, so this is RG. The pivot for our tension is just going to be L. So when I go ahead and plug in, we'll wind up with L times the force of tension times the sine of theta minus L over 2 times mg, sine of 90 is 1, so I don't have to care about it. Add L2 mg to both sides, add L2 mg to both sides. That'll give us L force of tension sine theta equals L over 2 mg. Divide each side by L sine theta, and we've arrived at the same answer. So we have our shortcut way of doing it, where we're just sort of thinking about it conceptually. We have our way of actually doing it carefully by like picking out the pivots, making our net torque equal to 0, solving it out. Honestly, especially because most of the times these would be multiple choice questions, either one is going to do you just fine. We've got 15 minutes left. Goodbye, YouTube. That was a 30-minute behemoth.